Hello and welcome. In this example, we're going to look at this high pass filter, and we are going to specify the voltage drop across R1. And so to do that, we need an oscilloscope. So we can do that with the fourth one down on the side right bar here is your oscilloscope. Or you can go to Simulate, Instruments, and then the fourth one there is also the oscilloscope. Try to get this oscilloscope specifically since it has differential probes and the 4-channel one will not. So for this one, we want to measure our source voltage on channel A. We don't necessarily need it, but it's a good comparison. So let's get our source voltage. We'll measure that all the way across here on the beginning of our source. This source is exactly like our function generator, except for it's an independent source that can only do the up and down waveforms there. And then the second side gets to go to ground, any ground. So we could put it over here, or we could place it on this ground as well. And then channel B gets to be around our resistor since that's what we're wanting to measure. And so we'll place this side on the front side of our resistor and the negative terminal for B on the back side of our resistor. And then we want to color the positive terminal of B a different color so that we can tell them apart. We'll make that a blue color there. And now we're going to measure that voltage drop. So let's double click on our oscilloscope and hit play on that. We're given a really small signal over here, so we need to zoom in. That's our time base. So we'll scale that down until we get it stretched all the way across. There we go. And we can stop that and move backwards in our signal here. We don't want to go all the way to the end because sometimes our capacitors don't like that. So we'll pick somewhere in the middle there. And we can measure the peak voltage off of our resistor. We know that resistor voltage is blue, right? So we want to measure the peak of our blue waveform. So look at this time constant though. This sloped line here is because of our inductor, right? It's filtering out voltage at lower frequencies and then allowing the higher frequencies to pass. And so we'll see that it, as soon as we rotate our signal high, that inductor comes to life and it eventually becomes less and less resistance until all the voltage gets dropped across R1. And then as soon as we change our signal again down, that inductor comes back to life. It says that it doesn't like that change in current until it finally gets used to it. Right, and that happens way down here. And so we've stretched our time constant out. And if you were to do the time constant calculations on this one, you'd see that they take almost the entire length of our signal to get to the full state of our time constants. Okay, so we want to measure the peak voltage on this. We can pull out one of our probe lines here. And you see that when we drag this probe line, it's actually following the red signal across the bottom with that little node. And the other one is doing the same thing. We don't want that. We want to double click on our blue line to transfer that. You can also right click on the oscilloscope screen and say select trace and select channel B instead of A there as well to swap that over. Okay, after that, we can click on our first probe line until this triangle at the top gets larger, right click and go to next Y max, right? In the direction we want to go to. So we're just to send it out to the next Y maximum. We could even click on the second one until that triangle gets bigger, right click and go backwards to the next Y max. And that kind of verifies that those signals are going to be at the same spot. And we see that down here, T2 and T1 subtraction for voltage on channel B is 0 because they are exactly the same, right? They're both 9.759 volts. And that is the voltage drop at peak, at maximum for this signal. All right, let me know if you have any questions.